Today we're going to talk about dynamic programming, and this is actually a subject that is going to take us 4 or maybe even 5 lectures. And don't ask me why it's called dynamic programming. No one knows. Someone just called it dynamic programming. There's nothing dynamic about it. So when we say dynamic programming, if I want to define it very informally, it's basically the art of avoiding repeated computations. Okay. And the quintessential example of this is the example that we saw in the very first session of this course, which was computing Fibonacci numbers. So we're going to go back to that. Let's say I have this problem. In the input, I'm given some number n. In the output, I should write fn, which is basically the nth Fibonacci number. Now, this number can get quite big. So let's say I want only the last 5 digits of it. So fn modulo 10 to the power of 5. Okay? So that I don't have to think about the size of my numbers. Now, we saw that the simplest algorithm for this is to just do recursion. So I can just have this function f that takes n, and it says if n is 0 or n is 1, return 1. Now you can define your base case however you want. Otherwise, just return f of n1 plus f of n minus 2. Now, we saw that this is terrible. We actually analyzed the runtime. We saw that the runtime is worse than the Fibonacci numbers themselves. So this is not great. But today we want to really focus on what makes this such a terrible algorithm. And we're going to use the ideas that we use for improving this algorithm to actually solve a lot of other problems. So what makes this algorithm terrible is that it just keeps recomputing the same things. So let's say that I want to calculate, for example, f of 5, the 5th Fibonacci number. What's going to happen? In order to calculate f of 5, I'm going to recursively call f on 4, which will call f recursively on 3, which will call f on 2. And I'm already regretting this, which calls f on 1, right? So when this recursive call is over, the value is returned back here, and then this one calls f on 0. And then we go back here. Now I have f of 2, I go back to f of 3. This also calls f on 1. Now this 4 called f on 3, it's also going to call f on 2, which in turn is going to call f on 1 and on 0. And then I have something similar on the other side. I have f of 3 basically on the other side. So as you can see here, I'm calculating the same thing many times. So for example, f of 0 is calculated here and here. F of 1 is calculated several times. Actually, let me do this side as well. So on this side, I have f of 3. And in order to find f of 3, I'm finding f of 2 and f of 1. But then for the 2 itself, I'm doing f of 1 and f of 0. So as you see, there are a lot of repeated calculations. And that's definitely not good. And you can imagine that if instead of 5, I was doing this for 100, I would just keep recalculating things that I have already calculated. So the whole point of dynamic programming is to say, don't do this kind of thing. Whenever you have any algorithm that is recursive, whenever you have, let's say, a divide and conquer algorithm or something like this, try to define your subproblems in a way that you can just calculate each one of them once. Okay? So here's a very simple technique that I can apply here. I can say whenever I calculate f of some n, I would just write that down in a dictionary and I would remember it. And the next time that I'm asked for the same value, I'm just going to look into the dictionary and return it instead of calculating it again. And this is what's called memoization, because It's like we're keeping a memo. Okay, so I'm just going to have some, let's say, array in this case. I'm going to have an array, let's call it memo, and let's say that it's a huge array, okay? And when I want to calculate f of n, I do exactly the same thing as before. I say if n is 0 or n is 1, return 1. Otherwise, find this value, that's my answer. So is f of n minus 1 plus f of n minus 2. Okay. But now I want to say before returning this answer, just write it in the memo so that you remember it, so that next time if you want to calculate f of the same value, you don't have to do it again. Okay. And actually, I could even do it in this case. Instead of just saying return 1 here, I could say that my memo for 0 and 1 is 1. Okay. And then I could remove this from here. When I calculate my answer, I write it in my memo. So I say memo of n is this answer, and then I return the answer. But now I'm going to change my code in another way as well, and it's right here. So when I enter f of n, instead of just trying to calculate it, I first ask myself, have I calculated this before? So I say if memo of n exists, if I have calculated it before, then just return it, return memo n. Okay. So this is a very simple technique to make sure that I calculate f of n for every n exactly once. I will never do it more than once. Now, this was the tree that I had before. Let's see what happens if I do it with the memoization. So I'm going to do f of 5. And when I want to calculate f of 5, of course, I'm first going to call f of 4, just like before. But f of 4 is going to call f of 3. And this is going to call f of 2. And this is going to call f of 1. And it's also going to call f of 0. But well, 1 and 0 are already in my memo, so they don't really call anything else. I just read from my memo. And when I have f of 1 and f of 0, I can calculate f of 2, and then that's added to my memo, so I will never calculate f of 2 again. So I come back here, I have f of 3. It calls f of 1, but that's already in the memo. So it reads basically these two, adds them together. So now I have f of 3. I write f of 3 in my memo. I go to 4. Now here, f of 4 needs f of 2 as well. But when I call f of 2, I see that that's already in the memo, so I don't keep recursing. I just return the value that I have in the memo. And this calculates f of 4. I come here. Now, in this case, I have to call f of 3, but again, I had f of 3 already in my memo, so it doesn't continue to recurse, it just returns the value. Now, here's the thing. If you look at these two, look at the tree here, look at the tree here. The tree here, the first tree is branching, right? And we've actually analyzed its size before. It was the runtime of this algorithm, and we saw that it's exponential, right? But this tree, this one doesn't really branch. So whenever I'm going to the right, I always get to a value that was already in my memo. So whenever I move right, I will never branch anymore. So the size of this tree is just going to be O(n), right? So if I want to calculate f of n, I will have this tree f of n minus 1, f of n minus 2, all the way to f of 1. And then from each of them, I have a call on the right side, but that one is already memoized. It's already saved in my memo, so I'm not going to actually do it again. So by just remembering what I have calculated before, my runtime actually reduces to O(n). Okay? So this is just O(n). Now, of course, in the very first session of this course, we also saw a different way of finding the Fibonacci numbers in O(n). And that's also what's called dynamic programming. So memoization is also sometimes called dynamic programming. Sometimes people think of it as a different technique. They're actually the same, kind of. The idea is that I don't want to recalculate the same values. Okay. So the other way we saw was that I can just create an array, right? I can just create an array F of some size, let's say n plus 100, whatever. And then I can say f of 0 and f of 1 are 1. And then I can say for every I from 2 to n, f of I is just f of I minus 1 plus f of I minus 2. Okay. Now, this algorithm, of course, also takes O(n) time. But why is this pretty much the same as the memoization? Because you can see that this array here is basically the same as what I was saving in my memo, right? It's just that I'm looking at it from two different perspectives. Here, when I'm doing the memoization, I'm thinking of it from the perspective of starting at a bigger instance and going to smaller instances. So I want the answer for this bigger instance, f of 5. And I say, in order to find this answer, I would first need the answer to 4 and 3. So I recursively go and compute them, but I remember them. And then when I have the answer to 4 and 3, I just add them together. That gives me the answer to 5. But here, what I'm saying is that, well, if I look at all of my subproblems, if I look at f of 0, f of 1 to f of n minus 1, I know in which order I need to calculate them. I can calculate them from the smallest one to the largest one. So I just do it like this. Now, a different way of looking at this is that I have a problem and I'm solving this problem by dividing it into some subproblems. Now, I always have a way, it's very much like divide and conquer, to merge the solutions for these subproblems to get the solution for the main problem, right? But then these subproblems also have some dependencies between themselves. So when I want to calculate f of 3, I depend on f of 2 and f of 1. So I have to always be sure that f of 2 and f of 1 are calculated before f of 3. But this problem of dependencies, having a bunch of things that have dependencies, we've seen this before. This is topological sorting. Okay, so basically, this is the situation that I have. I have a problem, and my problem consists of a bunch of subproblems. Of some subproblems. Okay, but I also know the dependency between my subproblems. So for each subproblem, I know that if I want to solve this one, I need the answer to these previous ones. Okay, so I know the dependency between my subproblems. And if this is the case, then I can just sort all of my subproblems in a topological order and then just solve them in the topological order, right? So here's the thing again. If I want to consider, for example, my subproblems here, suppose I want to calculate f of 5, right? F of 5 depends on f of 4 and f of 3. Right? So I can say that I have this kind of dependency in my subproblems. And then f of 4 itself, it depends on f of 3, but it also needs f of 2 to be calculated. So f of 2 and f of 3 should be calculated before f of 4. And then I have f of 1 here, which has to be used for both 3 and 2, right? And then I have f of 0, which is only used for f of 2. So if I look at my subproblems, these are the subproblems that I have. Of course, this is if my final problem was to calculate f of 5. You can also imagine that if my final problem is to just calculate some f of n, I will just have a similar graph, but larger, right? Now I can take any topological sort of this graph and I can calculate the values according to that topological sort, right? So for example, I can first calculate f of 0, then calculate f of 1, then f of 2, then f of 3, 4, and 5. So now, it's not necessary that my graph has only one topological order. Maybe I can sort it in many different ways. The thing that is important here is that whenever I want to solve one of the subproblems, I should already know the answer to the previous subproblems, the ones that are prerequisites of this one, right? So if I have several different sorts, that's also fine. But now, what is the difference between dynamic programming and memoization? Again, the difference is really not that important. It's basically like the differences between the different algorithms that we had for topological sort. So if I want to do memoization, I start from the end. I say that I want f of 5. In order to find f of 5, I have to find f of 4 and f of 3. So I say I recursively find them, but as soon as I found them, I will just write them down so that I don't calculate them. And then I say, because I need f of 4, I need f of 2 and f of 3, and so on. Okay, so the way memoization looks at this is that basically I have this topological sort and I'm starting at the end of the topological sort and making my way back. The way dynamic programming looks at it is that I have my topological sort and I start at the beginning of it and I keep going forward. So I just sort all of these things topologically. I say I compute them in topological order. I first compute f of 1, f of 0, then f of 1, then f of 2, and so on. Okay? Now, a very really important point here is that this only works if the dependencies between your subproblems do not have any cycles, right? Because if I have a cycle, then of course I cannot compute any of it. And we will see some examples of cases where you define something and you see that it actually has a cycle, and when it has a cycle, I just can't do dynamic programming. And we've seen this when we were talking about topological sort, that if we have a cycle, we don't have a topological order, so there's no way to do it. Okay, but now let me just give you a different algorithm. Oh, and by the way, in which cases can I just do recursion instead of this memoization or dynamic programming? I can just do recursion if doing recursion would never recalculate the same thing, right? That would be equally as good. But when does that happen? So here's the thing. If I do recursion, when I'm doing f of 5, I'm basically going in the opposite direction of my edges. I'm calculating f of 4 and f of 3. And then I'm calculating for f of 4, I'm calculating f of 3 and f of 2 and so on. So recursion is optimal if the paths that I have from each of my subproblems to the final problem is unique. If I have only one path from each of the subproblems to the final problem, then my recursion will calculate the result of that subproblem only once. And then I don't need to do dynamic programming or memoization or any of these things. And in this case, this doesn't hold, right? So from, for example, f of 3 to f of 5, I have a direct edge, but I also have a path that goes to 4 and then goes to 5. Because it's not unique, it means that when I'm doing recursion, I would calculate f of 3 at least twice, and that's suboptimal. I don't want to do that. Okay? So this view of dynamic programming also tells you when dynamic programming is unnecessary in some sense. So let's talk about this same Fibonacci problem. We've already seen a recursive solution. We've seen how to do it with dynamic programming or memoization. And the recursive solution was exponential time. These two were linear time. Can we do better than that? And it turns out, yes. So here's the thing. Let's look at it as a matrix problem or vector and matrix problem. So here's what I'm going to do. Let's say I look at f of n and f of n minus 1 as just one vector, okay? And I'm going to give this vector a name. So I don't know, let's call it x sub n, okay? Now, what do I know? How can I write x sub n based on x sub n minus 1? Well, x n minus 1 is just f of n minus 1 and f of n minus 2, okay? So I want to find a matrix that I can multiply here so that this equality holds. But I know that f of n is supposed to be f of n minus 1 plus f of n minus 2, right? So I can put just 1, 1 here. And f of n minus 1 is just f of n minus 1. So I can put 1, 0 here. Okay. So this is just another way of writing that f of n is equal to f of n minus 1 plus f of n minus 2. Okay. Now let me call this matrix A. So what I have here is xn is equal to A times xn minus 1. Okay. Now, of course, I can now expand this. So I can say this is A squared times xn minus 2. And so on. It's basically equal to A to the power of n times x, well, I want x1 here, right? Okay, so A to the power of n minus 1 times x1. And x1, of course, I know what x1 is, right? So x1 is just f of 1, f of 0. So in my definition, it's just 1, 1. If you want to start with 1, 0, you can also start with 1, 0. Okay. So if I want to calculate the nth Fibonacci number, it's enough to calculate this xn, and then it will give me the nth Fibonacci number, but it will also give me the n minus first Fibonacci number, but I just ignore that one and I just output the nth Fibonacci number, right? Okay, so I just need to take this simple 2 by 2 matrix A and raise it to the power of n minus 1. Okay, now, the simple way to do this would be to just calculate all powers of A. But we've seen before, at least for numbers, and we can do the same thing for matrices, that I can do this with log n multiplications, right? So I can have a recursive problem that finds, let's call it the powers of matrices. It takes some A and it takes some K. And let's say it returns A to the power of K. Right? How can I do this? Very simple. I just say, take my answer to be A to the power of K over 2, and then just multiply the answer by itself. Okay? And I also have to say that if K is odd, then multiply the answer by A. Again, this is matrix multiplication. And return the answer. And I'm also assuming that, like before, my numbers are not going to overflow. So just imagine that I take the last 5 digits of the numbers. And of course, I also need a base case. And my base case is that if K is 0, return the identity matrix. If K is 1, return A. Actually, you don't need the second one, the first one. Okay. Now, this one, it's going to do basically log K matrix multiplications, but my matrix is 2 by 2. So every matrix multiplication here is taking constant time because the size of my matrix is so small. It's a constant size matrix. So this whole thing is going to take log K time, and my K is n minus 1. So basically my total runtime is now O log n, which is much better than the ON that I had before. Okay. Now, but this one, as you can see, is a recursive algorithm. I'm not using dynamic programming here, and I'm also not using any kind of memoization. Now, why is that? Because let's see what I need to do. So if you look at an instance of, for example, let's say size 11, okay, when my K is 11. If I have this, what's happening in my recursive procedure? I'm finding a to the power of k over 2. By the way, I forgot to write this in a recursive way. So I want to basically call the same function, matrix power of a and k over 2. Okay. So the instance for k equal to 11 only depends on the instance with k equal to 5, which itself only depends on the instance for k2, which itself only depends on the instance for k1. So basically, if I create my DAG, if I create my directed acyclic graph, which shows the dependencies between the instances, between the subproblems, I can see here that there is a unique path from each one of these subproblems to my final answer. So this is one of those cases where dynamic programming would not make your recursion faster. Because even just doing recursion without memoizing anything or without first doing the topological sort and doing dynamic programming is already going to look at each subproblem only once. Okay? Nice. So we're going to see some more problems here. And by the way, another thing that is interesting here is that you can kind of see that this memoization is kind of like a DFS on this tree, on this directed acyclic graph. Because when I'm doing memoization, I'm starting from the biggest instance, and I'm just basically doing a DFS, except that I'm doing a DFS on the transpose graph. I'm taking the edges in the opposite direction. So I'm starting from 5, I'm going to 4 and 3 and so on. Okay, and kind of the difference between memoization and recursion is that memoization is like a DFS. I want to find f of 5. In order to do that, I just do a DFS from it, but with edges reversed. So I first find f of 4 and f of 2 and f of 0. Then I come back, find f of 1. Then I come back, find f of 3. So this thing is actually a DFS tree, right? But if I don't do memoization and if I just do the recursive algorithm, it's kind of like doing a DFS, but not marking any vertices as seen, right? So you will just keep seeing the same vertices again and again. So that's another way that you can see memoization is actually helping or dynamic programming is actually helping. And again, this also shows that if I have a unique path, then I don't need the memoization because it's like, if you have a tree, if your original graph is a tree, there is a unique path from any node to your starting node. Then when you're doing DFS, you don't have to keep track of which vertices you have seen because you're going to see every vertex exactly once. Okay, so there is a really nice conceptual relationship between these things. Okay, I have some examples here. Yeah, let's do this example that we did last time. So remember we talked about the problem of giving change. And that problem was that I have a bunch of coins of different values. And I also have some particular amounts that I want to pay. And the question is, what is the minimum number of coins that I have to use? Okay. But now I'm going to kind of look at a more general version of this. And this is called the knapsack problem. And this is how this works. So in the input, I'm going to tell you this. So it's called the knapsack problem because originally it was formulated like this. There is a thief who's going to a jewelry store and trying to steal some things. He has a knapsack. The knapsack has a limited capacity. And then you have a bunch of whatever jewels that you can store in your knapsack. And each one of them has a size or it has a weight, but it also has a value. So you want to stay within the capacity of your knapsack, but you want to steal items that have the maximum possible value. This is what I want to solve here. So this is what I'm going to say. In the input, I have a knapsack capacity. Let's call it C. and I also have n items. And item I has a weight and a value. So it has weight Wi and value Vi. Now, I want to take some of the items. So as my output, I want you to just give me a subset, let's call it S, of items. Now, these items should fit in my knapsack. So the sum of the weights of all the items that are taken should be less than or equal to the capacity of my knapsack. Okay, but I also want to maximize the total value of the items that I'm taking. So such that this happens and maximizes the sum of the values of the items. Okay. Now, in this particular version, I'm saying that I have a bunch of items and I have only one of each item. So this is usually called 0-1 knapsack because from each item I can take 0 or 1, right? But we will also see a version where you have many copies of each item, and then that's actually more similar to the change problem. Okay, so I want to define subproblems here. What are the parameters that I have? I have my capacity and I have my items. So if I want to define a subproblem, I can say my subproblems are problems in which I don't have the complete capacity. Maybe I have smaller capacity. And I also don't have all of my items. Maybe, for example, I only have the first K items. Okay. So this is what I'm going to do. I'm going to define, this is basically my memo or my DP table. And I'm going to say answer of K and I want to use something other than C. So whatever, let's say D is equal to the answer when my capacity is D and I only have the first K items. Okay. And I only have items 1 to K. So the question is, if my knapsack capacity was D and I only had items 1 to K, what is the maximum money that I can make? What is the maximum value that I can fit into my knapsack? Okay. And of course, my final answer in this case is just going to be the answer when I have all of my items and I have the entire capacity of my knapsack. Okay. So these are the subproblems that I want to define. So for every K and every D, I have a subproblem. Now I want to figure out what is the dependence between these subproblems. So I want to find some sort of a recurrence relation or recursive formula that connects my subproblems to, let's say, smaller subproblems. But at this point, I don't really have a definition of smaller because I mean smaller with respect to my topological sort. So I have to kind of solve the problem before I know which instances are smaller. But for this particular problem, it's kind of obvious, right? So if you have fewer items or if you have a smaller knapsack, it's a smaller instance. We have that kind of intuition here. Okay, let's see. So suppose that I just want to find a recursive solution first. So I want to write a function that takes K and it also takes D and returns the answer when I have the first K items and a knapsack of size D. Okay. So here's the thing. I have these items. I have item 1, item 2 to item K. And I want to put some of them into my knapsack. Now I can do a case for, I can say I either put the last item into my knapsack or I don't, right? So if I don't put the last item in my knapsack. How much can I make? Well, my knapsack capacity remains at D, but now I know that I'm not putting the last item, so I only have the first K minus 1 items. So I can just say that I take the answer for K minus 1 and D, okay? So this is my first case. Let's say C1 is this. Now my second case is that I actually put item K into my knapsack. But I can do that only if item K fits into my knapsack, right? Maybe I don't have enough space for item K. So I have to check that. I have to say if there is enough space for item K. So if the size of my knapsack is greater than or equal to the weight of item K, now I can put item K into my knapsack. And this is my second case. So I call this C2. Now, if I put item K into my knapsack, of course, I'm going to get the value of item K, right? So that's VK. But then I now have a smaller knapsack because item K took some of the space in my knapsack. But of course, I want to fill it out optimally. I want to make as much money as possible. So I'm going to have the answer of K minus 1. And now my capacity is D minus the weight of the case item. Okay. So I find C1, I find C2. These were the two cases that I had. And of course, I want to do the optimal thing. So I want to take the maximum of these two. So I'm just going to say here, return the maximum of C1 and C2. And by the way, before this if, I'm assuming that C2 is 0, okay? Now, this is a recursive algorithm, but it doesn't have a base case. So if I just run it like this, it will run forever, right? What is my base case? My base case is, well, either when I don't have any items or when my knapsack has size 0, right? So if I don't have any space, if the size of my knapsack is 0, then I just return 0 because I can't put anything in it. And also the other base case is that if I have no items, if K is 0, I also return 0 because there is nothing to steal, right? So now I have this recursive function. Now I have the exact same problem that I had for calculating Fibonacci numbers. And the problem is that I have these subproblems, and I'm going to calculate the answer to some of these subproblems over and over again. I'm just going to repeat calculating this. So I have exactly the same solutions as before. I can either memoize or I can use dynamic programming. Memoize means that for every K and D, when I find the answer, before returning the answer, I just write it down in a memo. And the next time that I'm asked for the answer on this K and D, I don't calculate it again. I just read it from the memo, okay? And well, dynamic programming would be to just find the dependencies between these. And I mean, in this case, it's kind of obvious, right? So the subproblem for K and D depends on the subproblem for K minus 1 and D, and also on the subproblem for K minus 1 and D minus something, right? So if I just sort my subproblems in the order of their K value, that's already a topological sort, right? So I can just do it in that order. So here's how I would do it. So the DP solution is that I create this answer array, which is a 2D array. And initially, I say the answer of D and of 0 and everything is 0. So I can just do this. I can say for every K from 0 to what was my number of elements, N. And then I can say for every capacity D from 0 to the final capacity C of my knapsack, just do this, right? So I'm just going to copy this because I'm lazy. And by the way, this is probably the only course where we like it if you're lazy. So if D is 0, I don't have anything to return, so I would just say, write it in this answer table. So the answer of KD is 0. And if K is 0, also, I don't have return. The answer of KD is 0. Otherwise, C1 becomes the answer of K minus 1 and D. The only difference is that my answer is now an array. It's not a function, right? And this one is the same thing. I just have to say, instead of calling a function, just read it from the table. And that's it. That's my, and oh, at the end, again, I don't have a return. So here I have to say that the answer for KD is this. Okay. So these two for loops, the only thing that they're doing is that they're making sure my sub-problems are visited in a topological order. So that when I'm calculating the answer for K and D, I already know the answer for K minus 1D, and I already know this answer as well. So as long as these prerequisites are calculated before I calculate the answer for K and D, I'm fine. Okay. Now, what is our runtime? Our runtimes are going to be the same if we use memoization or if we use dynamic programming. So here's the thing. My K is going from 0 to N. My D is going from 0 to C. And in here, I'm just doing a constant amount of work. It's a bunch of ifs and so on, and maxim. So my runtime is just O N times C. Okay. So my total runtime is O N times C. Great. So this is a very simple example of dynamic programming. Now, a lot of the times in this course, when I talk about dynamic programming, I just give you this part. I just give you the recursive formula, and I just assume that you know how to turn this into dynamic programming. Because again, as soon as you have the formula, as soon as you know that the answer for KD depends on the answer for K minus 1D and K minus 1D minus WK, and you know how that formula works, then doing the dynamic programming is pretty trivial. Just take all of your subproblems, have a topological sort, compute them in that order. That's all. So for a lot of cases, I wouldn't actually give you the topological sort. I would just give you the recurrence relation. Okay. Let's see. What other problem is nice here? Let me actually do this. So let's say that I want to find shortest path in a weighted directed graph. Okay. So my input is just going to be a graph G. So it has vertex set V and edge set E. And this is a directed graph. My edges have directions. And let's say that I also have a weight or a cost on every edge. So I have a function W that is taking every edge and just assigning a weight to it. And for now, I'm going to say that my weights can be any real numbers. Okay, so I can have negative weights now as well. I'm doing this because I don't want to let you use Dijkstra, right? Because if I don't have negative weights, we already know a solution. We know how to find shortest paths using Dijkstra. So I'm going to put negative weights there so that you can't use Dijkstra. And I'm going to also give you two vertices. Actually, let me call this C so that it's a cost. I'm going to also give you two vertices U and V. And as output, you have to write the distance from U to V. Okay. And let's say I want to solve this using dynamic programming. Now, how can I do this? Well, again, just think of how you can write a recursive solution and then think of how to turn that recursive solution into dynamic programming. So let's say I have a bunch of vertices. Of course, I have my vertex U, which is my source here, and I have a ton of other vertices in my graph, right? And just let's take one of these vertices. Let's take vertex I. Okay. I'm going to define d of I as the distance from vertex U to vertex I. Okay. So d of I is just the distance from U to I. Okay. Now let's see if I can find some sort of a recursive formula for this. So I'm writing a function d that is taking some I and it wants to return the distance. Well, the base case is very simple. The distance from U to itself, it's 0, right? Is it 0? So here's the part where things get interesting. I can actually have negative cycles because I said I can have negative weights. So it's possible that I have a cycle like this, right? And I can just start from U, take this cycle over and over again, and my distance would be minus infinity, actually. I don't like this. So let's say that I additionally guarantee for you in the input that G does not have a negative cycle. Because without this, you can't really do it. Okay, so G doesn't have a negative cycle, but it can have negative weights. Why can it have negative weights? Again, because I don't want you to use Dijkstra. Okay, so I can have negative weights, but this cycle is now positive overall. Okay, so if I have a function, let's call it di, which is giving the distance from vertex U to vertex I can say, well, first of all, if I is equal to U, just return 0. Because now I know that the distance from U to U is 0. I don't have negative cycles. Okay, but let's say I want the distance from U to some other vertex I. I'm going to do a case fork just like before. I'm going to say any path that starts from U and ends at I is going to have some last edge. So let's just do a case fork on the last edge of the path. So let's say I had some edges coming into it from a bunch of different vertices. Maybe call this one J1, J2, J3. Okay. So the shortest path from U to I is either going from U to J1 and then taking this edge to I, or it's going from U to J2 and then taking this edge to I, or it's going from U to J3 and then taking this edge to I, and so on. So I'm just going to do a case fork over this, and of course I'm going to take the minimum distance among all of them. So here's what I'm going to do. I say my answer is initially infinity, and then I say for every vertex J, such that there is an edge from J to I. Okay. I say that my answer becomes the minimum of whatever distance I had until this point, the minimum of the answer itself, and the distance to J plus the cost of the edge from J to I. Okay. And then finally, I'm going to return my answer. Now, this makes perfect mathematical sense. The distance to vertex I is basically the minimum of this expression over all vertices J that have an edge to I, right? But it doesn't make algorithmic sense. What happens with this recurrence? It might never terminate, right? So imagine if I have a cycle. So I'm going to look at the smallest possible cycle. Let's say this is I, this is J, this is K. I want to find the distance to I. And in order to find the distance to I, here I'm going to recursively call the distance to j. So the distance to I actually depends on the distance to j. But in order to find the distance to j, I'm going to here call the distance to k. So this recursively depends on the sub-problem, which is the distance to k. But now that one depends on the distance to I. So if I have a cycle in my graph, I'm going to also get a cyclic dependency between my sub-problems. And if I have a cyclic dependency like this, my recursive algorithm is just never going to terminate. Okay, so not good. But of course, I'm changing the problem all the time to make my algorithm work. So here I said that I don't want to have a negative cycle. Let's say I don't want to have a cycle at all. Okay, G does not have a cycle at all because I see that any cycle destroys my algorithm. So in other words, this is not the shortest path in a weighted directed graph. It's a shortest path in a weighted directed acyclic graph. So I have a DAG. Okay. And if I have a DAG, then this function works. Right? Because if I have a DAG, then I don't have a dependency between my subproblems. But again, my runtime is horrendous here with this recursive function. But of course, I can just look at my subproblems and I can order them in a topological order. Now, my subproblems in this case correspond exactly to the vertices of my graph. So all I'm doing is that I'm saying if I want to find shortest path in a DAG, I can first sort all of the vertices in topological order, and then I can process them from left to right. So this is the dynamic programming variant, DP. I say first, sort the vertices topologically. So I'm going to have all of my vertices. Let's say this is a topological sort. So all of my edges go from left to right. Okay. I might have a ton of edges. And I have my vertex U somewhere in there. Okay. And then I'm just going to go over my vertices from left to right. I'm going to say for every vertex I, for every V in the topological order, or actually let me call it I. So I have this vertex I here. I want to know what is the distance to I. I can just use the same formula as before. I can say the distance to I is the minimum of the distance to any predecessor of I plus the cost of going from that predecessor to I. So I just say for every J that is a predecessor of I, so I'm just going to write it like this, for every J that has an edge to I say that the answer for I, or the distance to I, and now this is no longer a function, it's an array because I'm doing dynamic programming. So I have an array of distances. I just have an array D of, let's say, size n, and initially everything is just plus infinity. Okay, so all of the distances are plus infinity, except that the distance to U itself is 0. Okay, so when I want to find the distance to vertex I say this is the minimum of whatever distance I knew before, and the distance to vertex J plus the cost of the edge from J to I. Okay. Now, this dynamic programming is doing exactly the same calculation that the recursive algorithm was doing. So since my recursive algorithm was correct, I hope that you believe that, then this one is also correct. The only difference is in the runtime, because this dynamic programming is not going to recalculate things that it already knows. So I'm basically starting from the left in my topological order, and I keep going right, and I keep finding distances to all the vertices. By the way, the vertices that appear to the left of U itself, they're going to have a distance of plus infinity, because all of my edges are going from left to right. And if a vertex is to the left of you, there is no way I can reach it from you. Okay. Anyway, what is the runtime here? Well, whenever I want to process a vertex I have to look at all the incoming edges that are coming into I, right? So this whole part, these two for loops, they're going to take O(n plus m). Because this one goes over all of the vertices, and just looking at each vertex is going to take O(n) time for me. But at every vertex, I'm looking at all the edges that are coming into it. And the sum of the number of edges that are coming into all the vertices is m. So this is O(n plus m. And of course, I need to also do a topological sort at the beginning. But we've seen that that can also be done in many different ways in the same runtime, n plus m. So my total runtime is just n plus m. Okay. But unfortunately, my algorithm here only works for acyclic graphs, right? So how can I extend this to algorithms on graphs that actually have cycles? Now you see, for the same problem, I can actually define my dynamic programming in many different ways, because I am the one who gets to decide how to divide my problem into subproblems. I'm the one who decided that my subproblems are going to be of this form. The d of I is the distance from u to I. I could also choose any other form. And the important point is that I have to define my subproblems in a way that makes sure there is no cyclic dependency between these subproblems. Okay, so let's do that. And by the way, this is again another example that I copied, I think, from Wikipedia. I hope it doesn't have copyright or anything. Yeah, okay, so I'm going to do one algorithm which is known as Bellman-Ford. Okay. This is actually probably the very first dynamic programming algorithm. Like Bellman was the person who invented dynamic programming, and he's also responsible for the name not making any sense. So my input is again a graph. Now this time I don't really care if my graph is directed or undirected. It actually works on both of them. So I have, let's say, a graph GVE. And as before, I also have weights. So I have costs on every edge, and my costs can be negative. I'm not going to add the problems that I had before. I'm not going to say I don't have cycles. I want to solve the general case of the problem where I can have cycles. And I can also have negative weights. I'm going to say I can even have negative cycles. Okay? But first, I'm going to start without negative cycles. Then we will talk about how it actually works even we have negative cycles. So I'm going to start without negative cycles. And I also have two vertices, u and v. And the output should be the distance or the shortest path from u to v. Okay, so exactly the same problem as before, except that I'm now allowing cycles. So I know that I cannot use the same way of dividing my problem into subproblems. I cannot use the same dynamic programming as before, because now that would create cycles, cyclic dependencies between my subproblems. But let me define it in a different way. So I'm going to do a casework on the number of edges. So in this case, because I have a weighted graph, the number of edges is not the same as the weight of the path, right? So when I say I want the shortest path, remember, I want a path with smallest total weight or smallest total cost. I don't care about the number of edges in my path. So for example, here from H to D, there is a path with one edge, but it costs 8. And there is this path with 2 edges that costs 4, and I would prefer this one. Now, I can do a casework on the number of edges that I have in my path. Here's how. I say, suppose I can reach vertex V from vertex U. If I can reach, I can definitely reach in at most n steps, right? Because if I have a path that takes more than n steps, by pigeonhole principle, it's going to visit some of the vertices more than once. There's going to be a vertex that is visited twice in my path. So my path has a cycle in it, and I can just remove that cycle from it, and all of my cycles are non-negative, so it gives me a shorter path. Okay. So generally speaking, this is always true for almost all of the graph problems that we look at. If you can reach a vertex, you can reach with at most n edges. Okay, so I'm going to say this. I'm going to say I have a function d, and it takes I, and it also takes some k. And what it returns is the distance from U to I using at most k steps, or at most k edges. So instead of saying, look at all the paths from U to I and tell me what is the shortest among all of them, I say you now have a limit on how many edges you can use. So I'm saying, look only at the paths that have at most k edges, and among all of these paths, find the cost of each path, find the one that has the smallest cost. And that's what I call d of ik. Okay, these are the sub-problems that I'm defining. Now, I can do something similar to here. So I can say, if I have a function that wants to calculate d of ik. Okay. First of all, let's do the base cases. What if my k is 0? It means I'm looking at paths that have no edges at all. So I can go from vertex U only to itself, right? So I say if k is 0, then it's very simple. If I is U, return 0. Otherwise, return plus infinity. Okay, and I use plus infinity to say that I cannot reach. Okay, so that's when I can take only one step or one edge. But in general, I can do the same argument as here. Let's say I want to reach vertex I. So I have this vertex I. And let's say that I want to reach it in at most k steps. So I want to find a path that goes from U to I, and it has at most k steps. Right? I can do a casework on the last edge of this path. I can say, look at all the edges that are coming into I, and the last edge of this path is one of those. So let's just take the minimum cost over all these cases. So I'm going to say, look at all the vertices J that have edges to I, and then d of ik is just going to be d of the distance from U to J1, but now I can take at most k minus 1 steps to get to J1, plus the cost of the edge from J1 to I. And then I'm going to take the minimum of this over all the J's. Okay, so very simply, here I'm going to say, well, first of all, I'm going to say my answer is just d of ik minus 1, right? Because if I ask you what is the smallest total cost to reach vertex I in k steps, in at most k steps, and if you already know the answer for k minus 1 steps, your answer cannot get bigger if I give you more steps, right? So I'm going to start from this. I know that my answer is either d of ik minus 1 or smaller than that. And then I'm going to say for every j such that there is an edge from j to I in my graph, the answer becomes the minimum of whatever it was before, and the distance to j, but using k minus 1 steps at most, plus the cost of the edge that goes from J to I. Okay. Again, the argument is exactly the same as the previous algorithm. The only difference is that I'm counting how many steps I'm taking. So previously, I just had d of I, the distance to I. But now I say, what is the distance to I if I can take at most k steps? So when I'm going to one of the predecessors of I, when I'm going to J, I can take at most k minus 1 steps. Okay, that's the only difference. But that actually changes everything. Why does it change everything? Because now I can look at the dependency between my subproblems, and I no longer have a cyclic dependency, right? Because if I look at the subproblem for I and k, when I want to find the answer for I and k, what are the subproblems that contribute to that? I need to know the answer for I and k minus 1, right? And I also need to know the answers for these j's and k minus 1. So I need like j1, k minus 1, j2, k minus 1, and so on. Okay? So if this is the case, then you see that I don't have any cycles, because every time that I have an edge, my value of k is increasing. Or in another way of looking at this is that dik only depends on subproblems that have a smaller value of k. So if I just sort my subproblems based on their k value, that's a topological sort. And I can do a DP. Again, this is the recursive version, which has a terrible runtime, unless you do memoization. But I can also just write a DP version. And in the DP version, I will have this array D, right, instead of a function. And then I just do this. But now I know that I have to do it in the order of increasing k. So I say for every k from 0 to n, and for every vertex I in my vertex set, just again do the same thing as here. So I'm going to copy this algorithm. And the only difference is that instead of calling things recursively, and instead of returning stuff, I'm just going to work with my array, right? So instead of saying return 0, I just say d of ik is 0. Instead of saying return plus infinity, I say d of ik is plus infinity. Here, I just have the array element, d of ik minus 1. And here, it's also just accessing the array. Right? Everything else is the same. And now, what is my final answer? Well, remember, I wanted the distance from u to v. But I didn't have any limits on the number of steps that I'm taking, but I also said that I would never have to take more than n steps anyway. So I can just output at the end the d of vn. So my number of steps k can just be n. So in the end, I just say output d of vn. Okay? This is what we call the Bellman-Ford algorithm. Now, I talked you through why this is correct, but what is the runtime? Now, generally speaking, when I want to find the runtime, I can again think of this dependency graph between my subproblems, and I can just imagine how many subproblems do I have, and at each subproblem, how much time am I spending? And then I can just sum this up and say that this is the total time of my algorithm. So how many subproblems do I have here? Well, for every k from 0 to n, and for every vertex I have a subproblem, right? So the number of subproblems is actually O of n squared, because this one has n possibilities, or O(n) possibilities, and this one is also O, right? Now, how much time am I spending for each one of these subproblems? Well, this part is constant time. right? And in this part, I'm going over how many edges? I'm going over at most n edges. I'm trying at most n different values for j, right? So this part is O(n). So I can say that my total runtime is at most O(n) cube, right? So total runtime is in O of n cube. Now I can do kind of a better analysis here, right? So here's how I can do a better analysis. I can say I have n different values for k. And then for every value of k, I'm going over every edge here exactly once, right? So for every k, I'm saying for every I, and then for every j that has an edge to I. So that means just for every edge, right? So this main for loop is doing n iterations, and in each iteration of this for loop, I'm going over each one of my edges exactly once. So my total runtime is actually O(n)m, where n is the number of vertices and m is the number of edges. Now, if you have a really dense graph, n cube and nm are not that different. But if your graph has few edges, then nm is much better than n cube. So actually, my runtime is O(n)m. And again, this is called the Bellman-Ford algorithm. Now, one thing that is interesting with our dynamic programming problems is that we don't always implement them the same way that we designed them. So, of course, I can implement this algorithm as I'm showing it here. But that's just going to take a lot of memory. And I don't like that, right? So how much memory am I spending? I'm creating this array D, and this is like an n by n array. I'm using n squared memory. So can I simplify this? Can I somehow make my algorithm simpler than this? I mean, of course, this is already simple enough to code. I expect that you should be able to easily code this at this point. But let me just take this and try to simplify it a little bit. Okay. Here's the thing. Just think of the distances that I had in my previous solution. In the previous solution, I wasn't really caring about the number of steps that I'm taking. So I just had the distance to every vertex. So let's say that I want to have an array that just keeps the distance to every vertex. So now di is the distance to vertex I. But it's not going to be the exact distance. It's going to be the best distance that I have found so far. Okay, so di is, this is pretty much like what we were doing in Dijkstra. Remember, I had some approximations of distances and they were not yet finalized. So they were just like an over approximation of the distance. So I'm saying that the di is the best approximation I have so far. Okay. And here's the thing. I'm going to do the same algorithm and I'm just going to drop this second part. So I'm going to say, because I have just the distance to vertex I, when I have 0 steps, the distance is just 0. When I have 0 steps and it's a different vertex, the distance is plus infinity. Otherwise, I start with the distance to I, and here I also drop that. Just say the distance to j. Now, this algorithm, of course, has the same runtime as the algorithm before, right? I didn't change the runtime. I'm just saying drop the second index in the array. So it's going to do the same thing as before. Now, why does it calculate the same answer as before? I want to claim that this is also Bellman-Ford and this is a correct algorithm. Okay. Now, here's the thing. First of all, what's going to happen? We said that as we increase k, as we give ourselves more flexibility on the number of steps that we can take, our distances actually go down, or maybe they remain the same. They cannot increase anyway, right? So if that's the case, then whatever I'm calculating here is going to be less than or equal to the distances that I calculated in the previous algorithm, right? Because previously, when I got here, I was looking at the distance of j with at most k minus 1 steps. But now I'm looking at the distance to j, and maybe it's the distance to j with k minus 1 steps, maybe it's with k steps, right? Because I'm not keeping track of the last index. Anyway, whatever I'm looking at here is smaller than or equal to what it was here. So the answer that I'm outputting in this algorithm for every vertex is going to be less than or equal to the answer that I was outputting in the previous algorithm. Okay, great. But I know my previous algorithm was correct. So my previous algorithm was outputting the correct distance. So all I'm saying is that this algorithm is under approximating the distances. The output of this algorithm is less than or equal to the actual distances. Now, I want to prove that the opposite also holds. The output of this algorithm is greater than or equal to the actual distances. And if I prove that, then I've proven that they're the same and the algorithm is correct. Now, here's the thing. When I set di to some value, it means that I found a path to vertex I that had that particular cost, right? Now, this path could have any length. But if that's the case, then whenever I'm doing this, the distance that I'm getting to vertex I is not more than the actual distance, is not less than the actual distance in the original graph, right? Because what am I doing here? I'm saying I had some approximation of the distance to vertex J. So I knew a way to reach vertex J with this cost, right? And then I'm just saying, take that way that I knew before and add the edge from J to I to the end of it. So this is now giving me a way to reach vertex I with this cost. So whatever I'm putting in my answer, it's going to be bigger than or equal to the distance to vertex I, right? So I proved both sides. I proved that the distance to vertex I is less than or equal to my answer and greater than or equal to my answer, so they're the same. And by the way, yeah, at the end, I forgot here to say that di should also become the answer, of course. And here too. Okay. So as you see, when I was designing the algorithm, I was thinking of doing dynamic programming, and my sub-problems included this k in them. But then later on, when I wanted to code it, I realized that I can just drop the k and my answer remains correct. Okay. So this was the Bellman-Ford algorithm, but we said this works if we don't have negative cycles. Now, what happens if I do have a negative cycle? Like, in which part of this algorithm, in which part of this discussion, did I use the fact that I don't have negative cycles? It was when I said that when I can go from U to V, I can go from U to V in at most n steps, in at most n edges, right? I said that the shortest path from U to V is going to have at most n edges in it. Now, if I have a negative cycle, that's the only part of my argument that doesn't go through. Because if I have a negative cycle, maybe the best way is to just go to that negative cycle and keep spinning, right? So this algorithm can be used to also find negative cycles. How can it be used to find negative cycles? Basically, if I do not have negative cycles, then I need at most n steps. At most n steps or edges. And this is in any shortest path. But remember that when I talk about shortest path, I'm talking about the total cost or total weight of the path, not the number of edges, okay? So it's shortest in the sense of cost. So if this is the case, it means that the distance to every vertex I with n steps is exactly the distance to vertex I, which means that if I have n plus 1 steps, I'm not going to get a smaller distance. If I have n plus 2 steps, I'm not going to get a smaller distance, and so on. So d of in will be equal to d of in plus 1, d of in plus 2, and so on. And this is for every vertex I. If I don't have a negative cycle, and I use this to say that my algorithm is correct. Now, here's the thing. I don't care about this part. Let's just look at this part. If I can have n steps or n plus 1 steps, my distance is not going to change. But if I do have a negative cycle, you can always prove that there is at least one vertex whose distance would change. If you have, you can use n steps or n plus 1 steps. Of course, I have to give a caveat here. If you have a negative cycle that is reachable from you, because maybe you have a negative cycle in a different connected component totally, and like you cannot reach that negative cycle from you, that's like not having a negative cycle, right? So when I say I have a negative cycle, I mean it's a negative cycle that is actually reachable. But if I have that, so if there exists some I such that the distance to I with n edges, and actually, I don't even need n edges, right? I need n minus 1 edges, right? Okay, I could do this with n minus 1 as well. Let's do it with n minus 1. Because I can see n different vertices in my path. That means that my path can have n minus 1 different edges. So I didn't need to do it up to n. I could just do it to n minus 1. You could also change all of these to n minus 1 in my algorithm. Doesn't matter. Anyway, if I have a vertex where adding one extra edge to my budget would actually make my distance smaller, then this tells me that there is a negative cycle. There is a negative cycle reachable from I. From you, sorry. The cycle reachable from you. So based on this, my algorithm works correctly if there is no negative cycle. And if there is a negative cycle, my algorithm reports that there is a negative cycle. I can just continue my algorithm for one more iteration, calculate all of these distances, and just compare them. And if there is a distance that is changing, it means I have a negative cycle.